Hi, myself Dr. Vinder Kumar. Today in this session, we will discuss about the graphs, path, circuit and related topics. Graph is mathematically representation of a network and it describes the relation between lines and points. A graph is pair of sets, say V and E, where V is set of vertices and E is set of edges formed by a pair of vertices. So here E is a multiset. In other words, its elements can occur more than once so that every element has multiplicity. In formal definition of a graph G is an ordered pair of V and E, where V is non-empty set and E is multiset of two element subset of V. So here V is a set of vertices. So element of V is called vertices or nodes and E is set of edges. So the element of set E are called edges. In mathematical notation, here G is equal to pair of V and E, ordered pair of V and E. So V is set of vertices. So V1 to Vn. So in this graph G, we have n number of vertices and E of G have edges. So E1 to EQ. So the number of edges we have Q. So let's take an example of EK. EK is equal to Vi Vj. So vertex Vi and vertex Vj. That means Vi Vj are called the adjacent vertices in the graph. So here we have example of graph. So here we have graph G with the pair of V and E. V is set of vertices and E is set of edges with 5 vertices and 6 edges. So the 5 vertices are A, B, C, D and E. These are the A, B, C, D and E. So E is a set of edges of this graph G. Then first edge is A to C, the vertex A to vertex C, vertex A to vertex C. So this is the one edge, A to B, A to D, D to E and same B to D. The 6 edges we have in this graph. So the degree of a vertex of a graph is the number of edges that are incident to the vertex, that is denoted by degree of that vertex. So in this example, here we have degree of A is equal to 3. So that's mean 3 edges are incident to this vertex A, 1, 2 and 3. So degree of C is 2. So 2 edges incident to C, 1, 2. So the degree of C is 2. So if we say the degree of D, that means 1, 2, 3, 4. The 4 edges are incident to this D. So the degree of D is 4. So next is path and circuits. A path is a sequence of vertices with the property that each vertex in the sequence is adjacent to the vertex next to it. A path that doesn't repeat vertices is called simple path. So here Pn is pair of V and E. V is a set of vertices and E is set of edges and Pn is a path. So the number of edges in Pn is n minus 1 and here number of vertices is n. Vertex 1 and n are called endpoint of Pn. So in path, no repetition of edges and no repetition of vertices. So second definition is about the circuits. Traversing a graph such that not an edge is repeated but vertex can be repeated and it's closed is called circuit. So here we have example for the path and circuit. So in this example we have the graph G with the V vertices, E edges. Here the vertices is 6 vertices and 8 edges. So V1, V2, V3, V4, V5, V6, these are the vertices, and edges from E1 to E8. So the path will be from V2 to V5. So V2 to V5, we have one edge E6. So V2, E6, V5, like this way. Then E5 to E4. E5 to E4, we have edge E5. So the V5, E5, E4. Then via E3 to V3. E3 to V3. So the we have path is like this way, from this to this. This is the path, and all the edges come in this path are also included, these edges. So in circuit is a closed, so the starting vertex and ending vertex are the same. So V2 to V5, V2 to V5, so V5 to V4, V5 to V4, V4 to V3 via E3, then V3 to V2. So this, so start and end on a same vertex. So this is called circuit. So here in this example we see the edge E4. The E4 is a loop, is a special type of edge that connected a vertex to itself. So next is Euler path and Euler circuit. An Euler path in a graph or multigraph is a walk through the graph which uses every edge exactly once. A graph has Euler path if and only if there are at most two vertices with odd degree. So second definition is about Euler circuit. An Euler circuit is an Euler path which start and stop at the same vertex. A graph has an Euler circuit if and only if the degree of every vertex is even. So here we have notation. The graph G with the pair of vertex V and E, and this E is, and this T is a trace from V1 to Vn plus 1, and in a circuit condition the Vn plus 1 is equal to Vn, because starting and ending vertex are same. So the Vt is equal to V and Et is equal to E in the case of Euler circuit. So here we have example. So first graph G with V vertices and E edges. Here we have 6 vertices and 7 edges, and this T is a trace or path from V1 to E7, and last again we reach on V1. So we start from V1 to V2, V2 to V3 to V4, and then V5 again on V3, V6. We traverse on all edges only once. So this graph has Euler circuit. So in this example, we have the graph H with V vertices and E edges. Here we have 4 vertices and 5 edges. This graph, the vertex V1 have degree 2, vertex V2, degree 3, vertex V4, the degree 3, and vertex V2 have degree 2. So according to definition, this graph is not follow the rule for the Euler circuit. The Euler circuit is a graph has an Euler circuit if and only if the degree of every vertex is even. So here we have 2 vertices V2 and V4. They have the odd number of degree. So this graph have Euler path but not Euler circuit. So this graph have Euler path only, like this way, not circuit. So by the definition of Euler path and circuit, we conclude Euler's path and circuit theorem. A graph will contain an Euler path if it contains at most 2 vertices of odd degree, And second is a graph will contain an Euler circuit if all the vertices have even degree. So here we have example. In this graph we have 5 vertices and 7 edges. The 5 vertices are A, B, C, D and E. So vertices A and C have degree 4. Since there are 4 edges leading to each vertex, B is degree 2, D is degree 3 and E is degree 1. This graph contains 2 vertices with odd degree. Those are D and E, and 3 vertices have even degree A, B and C. So the by Euler theorems tell us that graph has Euler path but not the Euler circuit. So this have 4 degree, 2 degree and this 4 degree, and these have odd degrees D and E. So the Euler path yes and Euler circuit no. Thank you. Hi, myself Dr. Kumar. Today in this session we will discuss about the Hamiltonian graph and planar graphs. So next topic is Hamiltonian path and circuit. Hamiltonian path visits every vertex once with no repeats, but doesn't have to start and end at the same vertex. On the another side, Hamiltonian circuit is a circuit that visits every vertex once with no repeat. Being a circuit, it must start and end at the same vertex. So by the direct theorem on Hamiltonian cycle, the statement that an n vertex graph, here n is greater than or equal to 3, in which each vertex has degree at least n by 2, must have a Hamiltonian cycle. And the second theorem is Orr theorems that come under light in 1960s. A simple graph with n vertices, here again n is greater than or equal to 3, is Hamiltonian if for every pair of non-adjacent vertices the sum of their degree is n or greater. So here we have Hamiltonian path and circuit examples. Here we have 3 graphs G1, G2 and G3. The first graph G1. G1 has no Hamiltonian path and no Hamiltonian cycle. So if we try here to start with any vertex like C, then C to B and D, then again visit on B, that is no have Hamiltonian cycle or path. G2 has Hamiltonian path A, B, C and D. So we start from A, then B and then C and then move on D. So this have Hamiltonian path but no Hamiltonian cycle, because we are not able to reach at the starting point without repetition of any vertex. So in G3 has Hamiltonian cycle. So in G3 we have Hamiltonian path and cycle both, like this way. So the next topic is planar graph. When a connected graph is drawn without any edge crossing, it is called planar. When a planar graph is drawn in this way, it divides the plane into regions that called faces or regions. So from the planar graph we derive the one formula, that is Euler formula. So it have a connection between vertices, edges and region. So there is a connection between the number of vertices, the number of edges and the number of region in any connected graph. That relationship is called Euler formula, and that relationship is vertices minus edges plus region always equal to 2. So now we try to prove this with the help of example. Here we have graph G with the pair of vertices and edges. Here we have two set, V is vertices and E is edges, and in set V the total 8 number of elements. These are the vertices: first, second, third vertex, fourth, fifth, sixth, seventh and 8th. So in V we have 8 vertices, and in edges we have 12 edges. So when we draw this graph in a planar, so it look like this way. No edge is crossing to any other edge. So by the Euler formula, there are total number of, so first of all we know the number of regions. This is the first region, second, this is third region, fourth, and this is 5, and this is sixth region. So there are total 6 regions with 5 bounded regions and 1 unbounded region. These are the 1, 2, 3, 4, 5 are bounded regions, and 6th is the unbounded region. So by the Euler formula, here VE plus R is equal to 2. So here vertices we have 8, total number of edges 12, and total number of region 6. So 8 minus 12 plus 6, we have 2. So by the Euler formula, what we need? 2. So here next example, the planar graph, a graph G with V vertices and E edges. V is equal to 6 and E is 8. So draw a figure is a planar graph which divides the plane into 4 regions. The regions are R1, R2, R3. These are the bounded regions. R4 is unbounded. So here we want to find the number of regions. So we write the formula like this way: R is equal to E minus V plus 2 is the Euler formula. So initially we have the regions 8, vertices 6 plus 2. So 8 minus 6 plus 2 is equal to 4. So the number of regions we have 4. The 1, 2, 3 and 4. From this formula, if we have any two things like vertex, edge, then we calculate the regions. If we have vertex and regions, we calculate the number of edges. If we have the regions and vertices, we can compute the number of edges. Thank you.
The topic is graph coloring using backtracking. Now, what is graph coloring? Graph coloring is the process of assigning colors to the vertices of a graph such that no two adjacent vertices of it are assigned the same color. Now, taking this example, there are now 5 vertices, and every vertex which is adjacent to every other vertex should be of different color. That means there the condition is the two adjacent vertices should not have the same color as shown here in this diagram. Now there is one type of problem in graph coloring, that is finding the chromatic number of a graph, that is denoted by psi of G. What is chromatic number? That is the minimum number of colors which are being required to color that graph, which also satisfies the property of that no two adjacent vertices should have same color. Now if you consider uh, this type of graph with 5 elements, no doubt this is supporting graph coloring because every color, no two adjacent vertices have got same color, but this doesn't have all the colors are being distinct here. But these are not the least number of colors. The least number of colors, if you try to paint it with one color, that is mustard one, adjacent will have different color. This is, let it be blue and blue here. You can give to this color mustard color, reason being this is not adjacent to either of the color, and this um, vertex can neither be given the color mustard or blue. So minimum number of colors which are required to paint such a graph is 3. That means at least 3 colors are required to paint this graph, supporting the property that two adjacent vertices should not have same color. Now generally, if some form of map is being given, how we can convert this map in the form of graph? For that, different regions are be given for a given map. That 5 regions are given. Now here, region 4 is adjacent to 5. Then we can make an edge from 4 to 5. In the similar manner, 4 is adjacent to 2. This region is adjacent to 2. We can create an edge from 4 to 2. Similarly, from 5 to 2 there can be edge. For 1 to 2 there can be edge, and so on. That means the given map, which is nothing but reflecting a set of regions, can be easily mapped to the form of a graph, where you can further apply graph coloring. Now there is second type of problem other than first problem, that is chromatic number problem. Second type of problem in graph coloring is called M coloring problem. What this M coloring problem says, that given a graph, that graph is given to you and given some m colors. M colors can be 1, 2 or 3. Check whether that graph can be colored with those given m colors. For example, if you are applying two coloring problem, that means if two colors are given to you, can we be able to paint this graph with these two colors exactly, satisfying the property that no two adjacent vertices should have same color. Now let us suppose partially we have filled in this graph. Blue color is being painted, red is being given here, and there are total two. When we will try to paint this vertex, it can neither be given red color nor be given blue color, because these two vertices are already adjacent to this new yet to be filled vertex. That means two coloring problem is not possible for the given graph. But the same graph can be colored using 3 colors. Now this is a representation of 3 colors where distinct blue color green will be used. Now third type of problem in graph coloring is, given a graph, and let us suppose it can also be painted by given number of colors, that is the least number of colors with which the graph can be painted, that is given to you. What are the possible ways in the which graph can be colored? This is the next type of problem. Now, for example, this graph is being given and two colors are being given to you. What are the possible ways in which we can color this given graph? These are the two ways. This either can be painted with the color green. This will be colored with blue. This will be colored again with green. This is blue, and these are two different patterns for the same. There is one more example for this. That means the problem is, basically we have to print all the possible color combinations for a given graph, where we know that these colors are sufficient to paint the graph satisfying the given property. But there is one more example. Given this graph, we have to paint this graph using 3 colors. What are the possible color combinations that are feasible as output? Now to paint this is one of the pattern. To color this graph is another pattern. To color this graph there is 1, 3 pattern. That means, now how backtracking can be used to solve the problem of graph coloring, that is to print all the possible ways in which the graph can be colored using given set of colors. Now a graph is being given and the given set of colors which are given me are 2. Now we'll be generating state space tree for the same. Now in this state space tree, we will be traversing accordingly to the way the graph is being painted. Now this is called the root node. It does nothing. It's the initial starting point from where the state space tree will start working. Now first node, when it is being painted, will be assuming that we are painting the nodes in this sequence, first green then blue, for the sake of simplicity. Now first node is being painted with the first color, that is the green color. There is no problem in painting because no other colors vertex has been painted yet. Now when you are trying to paint the B vertex, that is at level third level, you are trying to paint the B vertex with color B. When you are trying to print the B vertex with color green, it is not possible because it will lead to adjacent colors, because two adjacent vertices can't have the same color. Now that means this is coloring is not possible. Now backtracking will be done, and the B will be tried to be colored as blue, the second color, which is feasible one. Now after this, the coloring process of C starts. For C, the color, initial color to be given will be green, which will be serving the purpose, that is no two adjacent vertex is having the same color. It is satisfying the property of graph coloring. It can be painted with that. After that, we will be trying to paint D. D is given first color, which is green color, which is not possible because green here and green can't be here, because A and C both are already green. D is given another color, that is blue color. From here we are getting the first solution. Now again backtracking will be done, and this will, that means as you have explored all the possible colors for D, now you will have to explore the colors for C, another color, that is blue color. But blue color is not possible, the reason being both will become adjacent color will become blue, because both adjacent vertices will become of blue color. Now it will again do backtracking. That means you will try to explore for new value of color for B, which but B has already consumed its set of colors. Now we will backtrack and try to color A with blue color. That new color pattern is blue color. Now for once you have painted the vertex with blue color, now you will move further. You will try to give first color to the vertex B, that is green color, which is possible one, which is one of the permissible partial solution. And for the C vertex, when we are trying to give color as green, this will violate the condition of graph coloring, so it is not possible. So we will try with C giving the value as blue color. Now once the blue color has been given, for D you can give the color as that is green color can be given easily, that the first color. Now this will lead to second solution, the second solution which has been there. Then we'll try for the further with D as given as blue color, which is not possible. It will violate the property of graph coloring. And we can do backtracking, and further we can change the color for B also by giving it as blue color, which is also not possible. Now this was the whole procedure of generating two possible colors for the given example in hand. Now basically when state space tree is being used, and in case of backtracking, DFS search is being done. Now just see the position of the star, how DFS search is being done in case of backtracking. Initially the star is at root node, then traversal is being done at the level of this level of it reaches at node A, then it reaches at node B, then it do backtracking and reaches at second blue colored B, then it traverses this branch, then it moves to the last of this branch, then it backtracks and try to explore another branch of this subtree, then it move backward and it tries to explore the rightmost branch of the tree, then again it move backward and try to explore the right hand branch, that is the blue colored A. It explore left branch, again left branch, it go leftmost till end, and again backtrack and it go right branch, and from right branch it explores the left branch till end. Now it has explored the right branch, it will go to the now it has explored left branch, it will go to the right branch, and it will move upward and will go back to the right branch, which is the last remaining branch of the tree. In the similar manner, this is the way DFS search is being done for backtracking. Now, these are the two possible solutions which we have seen. The first solution pattern is permutation is green, blue, which is given here, and second solution pattern is blue, green. We can take one more example for the same. Now, this given graph can be colored into green and red. How it is being achieved? Both these are the possible patterns. Now, these are the possible patterns in which the graph can be colored. Now for coloring this graph, state space tree which has been made, that is this state space tree said we start with the initial root node, then the first node, that is the first node which is given in the internal value within the node, that can be given either of the color R, G and B. If the first node is given in the color red, the second node can be given the color green or blue. If the first node is given color red, second is green, then third can't be given either red or green because both are adjacent to the 1 and 2. In the similar manner, we can draw the state space tree for any graph and apply backtracking problem to solve the same. Now the general input for finding the graph coloring problem is you have to input the graph in the form of adjacency matrix, and you have to tell the number of colors which are being required to paint that graph. The output will be a matrix which will represent the number of colors in the form of indices like 1, 2, 3, that will represent different colors in which the different vertices have been painted. From backtracking, if you try to summarize for graph coloring problem, these are having some broad steps. If the colors are assigned, print those assigned all the color vertices. Otherwise, try all the possible colors and assign the color to the vertex. If no assignment is, if color assignment is possible, recursively assign the colors to next vertices. Otherwise, de-assign the colors. What is the meaning of de-assigning the color? Means if you go in detail for the steps of backtracking algorithm for graph coloring problem, the broader steps is confirm whether the color is valid color for a given vertex which you want to color. That means then no two adjacent vertices should have the same color. If validity is being approved, then color it with the same. Otherwise, try with the immediate next color. If no color is available for that, then you can go for backtracking. That means you can backtrack. Uh, If no color is available, then you can do backtracking, that is uncolor the last colored vertex and return false. After each coloring, check if all colors vertices are colored or not. If yes, then return program should. If yes, then program should return true. Otherwise, it should continue with coloring the rest of the vertices. Now selecting only one, after that we will be choosing next uncolored vertex and repeat the. Now if you try to conclude this whole of the process of graph coloring, basically we will starting with a single vertex, then we will move into adjacent vertex. We will color that adjacent vertex with the color which has not been given to the rest of the connected vertices. After coloring, we will then move to the adjacent vertex which is colored further. We will repeat this process. Now backtracking here means that we will stop further making any recursive call on the adjacent vertices. That means how to stop making those recursive calls by returning the value as false. Backtracking means that trying for a different color option for the immediate last colored vertex. The topic is M coloring problem. Now what is M coloring problem? It says given a graph and given the number of colors, and those number of colors are say m, is it possible to color the given graph with those set of m possible colors or not, such that it holds the property that no two adjacent vertices have the same color. This is also called the term M colorability problem. Now, how to apply backtracking to check for M colorability? Now, given this example, different let us suppose seven vertices have been given for a given graph. This adjacency matrix for the same one, C2, C3. They have been named colors like first color is C1, second color is C2, third color is C3. Now we start the algorithm by painting the very first vertex V0 onward. Then next we'll be painting V1, V2, V3, V4, V5, then V6 and V7 in the same sequence. We are assuming that we are trying to paint the given vertex with the colors that to choosing the colors in the sequence. That means first we'll try to paint a given vertex with C1 color. If it is not satisfying the property of graph coloring, we will try to paint the same with C2 color. Then if it is still not satisfying the property, then we will try to paint the same with C3 color. Now let us start the same. Let us suppose vertex V0 is being painted with C1 color. There is no other adjacent vertices which have been painted yet, so it can be easily painted. Second thing is, choose the next vertex, that is V1, and you can color you cannot color that vertex with C1 because C1 that vertex V1 is adjacent to V0, which is already painted with the color C1. So the next immediate color for V1 will be C2. Now for V2 color. Now for V2 color, we can't paint V2 with C1 color because V0 is already being painted, it's adjacent to V2. We can't paint V2 with the color C2 because the vertex which V1 which is adjacent to V2 is already painted with C2 color. So the next possible color for V2 will be C3. Now considering vertex V3, now V3 can be painted with either of the color because all the adjacent vertices to these are not being painted so far. So the V3 can be painted directly by the first color, that is C1. Coming to vertex V4, now V4 is connected through V0, that is C1 color is not possible. V4 is connected to V1, that is C2 color for V4 is not possible. V4 is connected to V3, but here the color is C1. That means the third color possible for V4 is V3. Now coming to the vertex V5, V5 cannot be assigned the color C1 because adjacent vertices has got the color C1. It can be assigned the color C2. Considering the V6 vertex, V6 can neither be assigned the color C1 or C2 because adjacent vertices do have the color of the same. V6 is assigned the color C3. Similarly, going for V7, V7 cannot be given the color C1 or C3, so it will be painted with the color C2. Now this is the whole procedure. Now this is the whole procedure for applying backtracking for checking M colorability. Basic idea for this is that is we should assign the colors one by one to different vertices starting from the vertex 0. Before assigning a color, check for safety by considering already assigned colors to the adjacent vertices. That is, check if the adjacent vertex have same color or not. If there is any color assignment that does not violate the conditions, mark the color assignment as part of the solution. If no assignment of color is possible, then backtrack and return false. That is the whole process of backtracking for checking the M colorability problem. Now different application of graph coloring, it can be used for scheduling purpose, like for example timetable scheduling, for frequency assignment, for register allocation, for bipartite graphs and map coloring, etc. There are many applications of graph coloring approach. That's all for this session. topic is graph coloring using backtracking. Implementation steps. Now, before starting with the implementation part of the graph coloring using backtracking, let us take an example. Say, given graph is being given, and let it be it has been colored by using backtracking method, where red color is represented by 1 value, green by 2 value, blue by 3 value. Now, what output we'll be getting after graph coloring using backtracking? This will be getting a final matrix in this form. This final matrix states that zeroth index vertex, that is zero vertex, is being colored with one, that is the red color. One is being colored with the color green, that is color number 2. Two vertex will be colored with the number colored as 1. Three vertex will be colored with the number colored as blue. That means this is nothing but the array containing the numbers representing the color of the blue with respect to all the vertices of the graph. Now let us take an example to know the concept of how this problem is being implemented. Now take the same graph. Here the number of nodes are 4 and the possible number of colors with which the graph has to be colored is 3. M is the number of color. The equivalent adjacency matrix for the graph is this one. Now this is the main underlying algorithm for coloring the graph. Now there is another subsection of this code that is called to check whether the vertex is being colored safely or not. Safely means the vertex is colored with such a color such that no two adjacent vertices have the same color as that of the painted vertex. Now, how this whole simulation take place? The main part of the algorithm is graph color function. It takes into the as an input the index of the vertex which is to be painted yet. Now we start with the zeroth vertex. We will give the index of the vertex which is to be painted as 0 to this function graph color. K value is given as 0 value. Then after sending the vertex which has to be colored, this function will start to apply the colors in using a for loop one by one. That is, first color will be applied will be tried for that vertex. If first color is a safe color for that vertex, that color will be assigned. Otherwise, the system will try for the second color, and that means it will be exploring for all the possible number of colors. Initially, this is the only vertex which is to be colored. So first color number C1 is taken as red. So that and how to check whether it is a safe state or not? There is a function called isSafe. IsSafe function takes the um, number of the vertex into account along with the color. That means vertex number and the color is being fed to the safe state function. That is the vertex number and the color to be painted is fed to the function isSafe function. Now what this isSafe function does, it tries to find for a given vertex, it tries to find all the adjacent vertices to that vertex and check whether the color which we want to assign to this k index vertex, whether it is already there for the adjacent vertices or not. If the adjacent vertices has got the same color as that of the color which we require to paint for the given index color, that is k index color, k index vertex, then it will be returning false. That means because no two adjacent vertices can have the same color. Otherwise, this will return the function as true. So because this is the very first vertex which has to be painted, so no adjacent vertexes have the same color because they have no other vertex have been painted yet. So it isSafe will return true in this case. Now once isSafe returns true, what is the second line for the same? Second line says xk is equal to c. That means we have to fill in that array which is the final output array. That means x0 will be equal to 1. That means first index vertex, zeroth index vertex will be painted with red color safely. Now moving to the next, once it has been first vertex has been painted, The algorithm starts for if k plus 1 is less than and still the vertices are left to be painted. Then again recursively graph color function is being invoked. Now the argument which is passed is the immediate next vertex index, that is the value being 1 here. That means we have to now paint for the second vertex. Now painting for second vertex here is when we are trying for k is equal to 2, is safe function will not return true for first color because that has been already been assigned to the zeroth vertex, and as zero vertex is adjacent to one vertex, then we can't assign the first color to the second vertex. We cannot assign and the c is equal to one color to the vertex with number 1. Now the for loop will move further and will try for c is equal to 2. C is equal to 2 means the color being green. Now is save states a function. Now is save function will return the value as true. Reason being no adjacent vertices to this vertex has been assigned green color. So this function that xk will be assigned the value is c. That means x of 1 will be assigned the color 2. 2 means green color. Again, in the similar manner, graph color function will be invoked and so on. Now, what is the complexity of this graph color function? If n is the number of nodes and m is the number of colors, then time complexity of the algorithm is order of m raised to power n. That means different combinations of m raised to power n colors will be explored for n different nodes. Similarly, the space complexity of the same algorithm is order of n. We are assuming space complexity in terms of the final output array, that the array which is used to store the number representing the colors which is with which that every respective vertex has been painted. That's all for this session.
Hi, myself Dr. Vinder Kumar. Today in this session, we will discuss about the isomorphism. In isomorphism, we talk about the isomorphic graphs. If two graphs which contain the same number of graph vertices connected in the same way are said to be isomorphic. In more formal definition of isomorphic graph is the simple graph G1 with the ordered pair set V1 and E1. V1 is the set of vertices and E1 is the set of edges. And in graph G2 with the ordered pair set V2 and E2. V2 is the set of vertices and E2 is the set of edges of graph G2 are isomorphic if there is a bijective function f from V1 to V2 with the property that vertex A and vertex B are adjacent in G1 if and only if the f of A and f of B are adjacent in G2. So next is the necessary conditions for any two graphs to be isomorphic. For any two graphs said to be isomorphic, if the following four conditions they satisfied, then we say those graphs are isomorphic. So the first condition is number of vertices in both the graph must be same. Second, number of edges in both the graph must be same. Third is degree sequence of both the graph must be same. Last, if a cycle of length k is formed by the vertices v1, v2 to vk in one graph, then a cycle of same length, that length is k, must be formed by the vertices corresponding to the second graph, like f of v1, f of v2 and f of vk in the second graph. So here we have one example. Here we have two graphs, one is G1, second is G2. The graph G1, the graph G2. G1 have V vertices and E edges, G2 have V dash vertices and E dash. In G1 we have 5 vertices, in G2 again we have 5 vertices. Check whether the G1 and G2 are isomorphic or not. So for isomorphic we have 4 conditions. The first condition is number of vertices are same in G1 and G2. In G1 we have 5 vertices, in G2 we have 5 vertices. Second condition is number of edges, that is 6. So here we have 1, 2, 3, 4, 5 and 6. 6 edges in G1, 1, 2, 3, 4, 5 and 6. The 6 edges in G2. Condition 3, degree sequence is the same. So the degree of A is 2, E is 2, C is 2. So here corresponding T, Q and S, they have degree 2, 2, 2. The only vertex D and B, they have degree 3, and in graph G2 the vertex P and vertex R, they have degree 3. And last condition is condition 4, 3 cycles of length. In graph G1 we have 3 cycles, the length 3, 4 and 5, and the same in the graph G2 we have 3 cycles with the length of 3, 4 and 5 are found. So here the first cycle 1, second cycle and third cycle, the length 3, 4 and 5. And in this we have first cycle here T, P, S, Q, R and again T. So here 1, 2, 3, 4 and 5. This is a cycle of with the 5 edges. So one is here the cycle with 4 edges. We start from P to S, S to Q, Q to R, R to P. So 4 edges included. So all 4 conditions are true here. Hence the necessary conditions satisfied, but still the graph need to have the same adjacency matrix. For that, so here we check the two graphs G1 and G2 are said to be isomorphic graph if their geometric duals are isomorphic. The vertices B and D in G1 has degree 3. Similar, the vertices P and R in G2. B and D in G1 and P and R in G2. So B and D in G1, P and R in G2. So f of B is corresponding to this P and f of D is corresponding to R. So here vertices A, E and C in G1 and T, S, Q has degree 2 in G2. So f of A is corresponding to Q and f of E is corresponding to T and f of C corresponding to S. Now adjacency is preserved for all the vertices, hence G1 and G2 are isomorphic. So here we have one more example. Here the graph G and graph H. With the graph G have 8 vertices and 12 edges. The same graph H have 8 vertices and 12 edges. So the corresponding f of A is corresponding in graph H, we have the node 1. So in graph G, the vertex G, the corresponding vertex in H is 5. So let's take this, the vertex I in graph G is corresponding to here the graph H has the vertex 4. So these two graphs are also isomorphic, G and H. Thank you.